Hey everybody, welcome to today's Kubernetes Master Class, where we are thrilled to have somebody from StorageOS here. We're going to talk about how to do persistent storage on Kubernetes and Rancher and how to do fast database recovery. I'm going to talk kind of slowly for a second as people trickle into the webinar, and then we'll do some basic announcements and we'll get started. It's my favorite part, the part where I talk like I'm a tape recorder on slow. All right, if they're not here yet, they can figure it out because honestly, it's not that difficult. So here we go. We expected to have both Alex and Farhan here today, but Alex had a prior engagement, so it's just going to be Farhan, and that's super cool because he is hands-on, neck deep in StorageOS, and the guy that is going to give us, I think, the best possible demo that you can get today. So my name is Adrian Goins. I'm the guy down there on the lower left. I'm an engineer at Rancher. I do all sorts of stuff, but for today, I'm just going to be your host. This is our Kubernetes Master Class series where every week or two, depending on frequency and scheduling, we try to give you guys some real good, actionable information that you can use for Kubernetes. It's not just Rancher specific. We bring in partners, we bring in technology providers that we think have great value to offer the community. But if you've ever been to a Rancher webinar, you know that these things, despite our best efforts to keep them to 40 to 40, it's not going to be that. We've got 90 minutes blocked out. I'm going to stop yammering here in a second. We are recording this, so if we go long and you have to drop off, don't worry about it. You're going to get a link afterwards that tells you where you can view or download the recording, so you're not going to miss anything. There's a tab or a thing somewhere in the GoToWebinar little UI widget where you can ask questions. Throughout the webinar, while Farhan is speaking, I'm going to be the one that's going to be answering questions, or I'll flag some for him to answer later. So just as things come to mind, ask away. Invariably, we will do our best to stay until all questions have been answered. And as it says here in this last bullet point, we tend to respond to questions publicly. So if your question is private, and honestly, I've never seen anybody ask a private question, but if you have a question that you'd like an answer for and you don't want me to share it with the community, just indicate that it's private and I'll keep it private. Yes, so this session is being recorded. I already said that. We have a YouTube channel. That's great. You can find it there. You'll get a link. Let's move on. If you're not already a member of our Rancher users Slack, this is a place where Rancher users and Kubernetes people and also Rancher staff hang out. We have a dedicated channel where we have conversation going on throughout the masterclass. You see that? That's #masterclass. So join that and you guys can make fun of me during the entire presentation. If you're not registered, over on the left there, you can see you can go to slack.rancher.io, enter your email, get an invite, and you too can join the party. We have several upcoming classes on, well, as you see here, on some really cool stuff. So alerting and visualization with Prometheus and Grafana. Jason Van Brackle is our director of community, really, really sharp guy. And then we have two more partners joining us for the following classes. So we can talk about streamlining deployment of global edge applications with Packet, and then DR strategies from Portworx. I'm not going to say anything more about Portworx because they're a StorageOS competitor. Oh, you're not supposed to see that slide yet. That's my last slide. All right. So with that, I'm going to shut up and I'm going to hand this over to Farhan. Farhan, are you ready?
Yes, I am. Hello, everyone.
All right. So I'm going to make you the presenter. And
yeah, I got it.
I'll let you know when I can see your slides. We have your slides. All right, my friend, take it away.
Let me just check once that also we're moving around and you can see.
Yeah, I see the browser now.
All good, fantastic. Thank you, Adrian, for the introduction. Thank you for hosting these to the Rancher guys. So today we're gonna talk about stateful applications, but first, my name is Farhan Arau Castell. I work in London. I work at StorageOS. I'm an engineer. We're gonna then move into the technical stuff. Thank you, Adrian. And again, during the slides and during the demo, I'm sure there are going to be many questions. Just please put them on the channel and we will go through them. So let's start. So First of all, today we're going to talk about databases, but mainly about the stateful applications, and stateful applications in the way that are handled by Kubernetes. Good. So first of all, I'm going to do a very, very brief intro on how state is managed or asked from Kubernetes to the system. And then we're going to move to a bit more interesting problems like productionized databases. So first of all, we're going to talk about the storage class. This is something that most people is not completely familiar until they need it. They know that they can use GP2 for Amazon or the Google disks or different, storage classes maybe for Ceph, but they don't really know what it is. So let's go a bit into it. Storage class is a way for an operator to define Kubernetes ways in a very declarative way how storage looks like. When we have a storage class, and we can have many in our Kubernetes cluster, we will create the persistent volumes, and we'll be able to use those classes. So a storage class is no more than a YAML definition in Kubernetes as any other object that pretty much can define parameters. In NFS, for instance, you could have certain addresses. With GP2, maybe you can define which class, or in Amazon, you can define which class of this do you want, etc. Once you have the storage class, you can ask for a persistent volume, or you can ask for a persistent volume claim that will map to a persistent volume. A persistent volume is pretty much the definition of a hard disk. If you think of disk in the traditional way, is a way for Kubernetes to know that there is a resource in the cluster that is a disk. This has evolved, and actually at StorageOS and all the other people that is doing storage for Kubernetes these days, we are evolving this this principle. But if you think about it, it's a disk. Developers or not system administrators can access and can do claims. So for every disk, imagine that you have 1 terabyte of data in one hard disk plugged in your node, in one of your Kubernetes nodes, and then you say, okay, I'm a developer, I need a chunk of this data, I need a chunk of this space to deploy my database. Then as a developer in a namespace, you can define a persistent volume claim. That persistent volume claim is just a definition that asks the system, hey, I need, in this case, 100 gigabytes of data. When this has happened, the persistent volume claim gets bounded to a persistent volume that actually is provisioned by a storage class. And now we have a way to map applications to disks, or applications to segments or sections of disks. And thanks to Kubernetes and its own design, this is pluggable. So I'm going to do a small intro of what StorageOS is to give you context, but we're going to move really fast into the problems that we have with the stateful applications or StatefulSets in Kubernetes. So StorageOS is a software-based defined network, defined storage system that pretty much allows you to decouple the understanding of a file system mounting in a container and the backend where the data is being written or read from. And I will show you what are the problems that we have solved and why this is really actually interesting. And it's not nice that I say that, but it's actually really cool, the way that we're trying to solve things. So StorageOS installs as a daemon set. We have a cluster operator that I'm going to use today to easy operations, but pretty much you get the concept that StorageOS deploys as a container. So we have a rancher server, and I'm going to use a deployed Kubernetes cluster. I'm going to use 2 clusters today. One, actually both are in Amazon, and we're going to install StorageOS as a container with that daemon set. So let's go and let's do it. So I'm going to use T1 and T2. Both clusters are in Amazon, and to avoid mixing around, I'm going to use first one and then the other. So let's install StorageOS. It's as easy as deploying an application. StorageOS, as I mentioned before, uses the cluster operator that we have implemented, and by the way, that operator is open source and will help us. And we want to install now with the minimal installation possible. So without barely touching any defaults, I'm going to start a cluster. I'm going to define a username and password for the first to start StorageOS, but pretty much we can have a lot of tuning here, but we actually don't need it at the beginning. Let's put something simple. And actually, I want to deploy StorageOS in the worker nodes. Rancher always add these labels. We can define them when we provision the cluster, but pretty much we want StorageOS to deploy in the worker nodes. So let's add the label. So pretty much with minimum configuration, I'm just going to go on launch. And hopefully I haven't messed with the label. So now the StorageOS operator starts. What is that? That is just a pod, right? It's just one pod that will start StorageOS and actually will handle custom resources. What is a custom resource? A custom resource is an object that defines a way or defines a Kubernetes object that we as StorageOS engineers define. So let's go and check that out. So what is a custom resource? A custom resource is no more than a definition of a cluster, and with that, the operator will do everything it has to do. For instance, we're going to use container storage interface as is enabled. There are images. If you have your private registry, you can start defining the images you need to use, etc., etc. There is a lot of information, but this is decorated by the operator with a minimal installation that we have done. So now let's check out actually what we were mentioning before about the daemon set. So we need a pod for every node of our cluster. First, let me show you the nodes. By the way, I forgot to do that. So in this particular cluster, we have what we would say one master node, and so the etcd is in one node, the control plane is in one node, and the rest are workers. So pretty much there are 3 workers, 1 master. As we can see, StorageOS has started. We can see the daemon set here, 1 per node, 3 nodes up and running, and a few other things that actually I'm going to talk. I'm very proud, actually. I'm very excited to talk about this header today as well. Okay, so now it's installed. How do we provision storage with this? How do we use this? Well, let's go to the command line. I'm going to use a repository and some resources here. They are completely available. They're all public. So just check this out. It's a GitHub repository in the StorageOS account, and everything is here. So I have a few examples here: PVCs, storage classes, etc. So first, let's check the storage classes as we were mentioning before. What do we have? We have 3 storage classes: the GP2, which is the Amazon one for EBS, and actually 2 StorageOSs. One is created by default, so you have that, and one that I created before to use that as well. So how a storage class looks like. As we mentioned before, just a YAML, and here we can start defining interesting information, for instance, how many replicas we want for our volumes, or some relevant or meaningful information. How a persistent volume claim looks like is something of the same. So check out volume claim. We're going to use that storage class. That's all we need to do. I'm going to use K instead of kubectl to make things faster, but I guess everyone can follow. Cool. Yeah, persistent volume claim, stream provision, and now it's going to be showing at StorageOS. So if we go to Rancher UI again, let's say, okay, now I want to see the StorageOS UI because I want to make sure that actually you can access through the CLI or the UI. So let's go and check out the interface. let's go one of the nodes. As I mentioned before, they're in Amazon. It's a public IP. Yeah, they are public IPs because I'm doing this demo. Maybe copied that wrong. Might be out. Let me check. Yeah, I'm in the right Wi-Fi. I can use the other one, no problem. I have another cluster that I'm going to use later, but it's already there. So pretty much persistent volume claim, we have a UI. We can see actually the volumes that are available. So now we have installed StorageOS, and that takes usually roughly a minute and a half. Probably I'm being a bit too impatient, that's why I cannot see it in the UI. But pretty much after that starts and a minute passes, a few health checks pass, and then we can start using StorageOS. So inside that container that we just deployed, we have two main components, the control plane and data plane. The control plane is what we could say it's the brain, and that brain talks to Kubernetes, all that interaction. It decides where the data is going to live. If the data is going to live in node 1, node 2, or node 3, or any of this kind of scheduling information or decision need to happen. There is a lot of orchestration in the cluster regarding, for instance, when the nodes spin up or all these kind of operations. The data plane, on the other hand, is a full-fledged storage engine. We have implemented in C and C++ a storage engine that decides at every single bit that the application sends to the storage system how we read and write this data. Where do we read? Where do we write it? All the consistency is implemented at our data plane level. We can do encryption or compression. There is a lot of functionality put on there. So now, let's start talking about the problems that we have with StatefulSets. So I gave you an overview of StorageOS because to understand the solution, I wanted to give you context. But let's go and understand what is the problem. So when we deploy an application, we can use a pod, and actually map that pod to a persistent volume claim, right? But the main issue here is that a pod doesn't have a life cycle. A pod is a unique identity that is not designed to run for a long time. So what we use is Kubernetes controllers. For instance, a deployment, a job, a cron job, stateful set. And that stateful set is very similar to deployment controller, but it has small differences. One of the differences is the way that the pods look like. You know that in deployments, the pods are the name of the deployment and some random string attached to it. Stateful sets, however, always conserve the same name, which means that you can start referencing them by name. So when the pod is restarted or the pod is dead and starts again, the name is held for access purposes. And that means that you can start mapping those DNS names into your applications. For instance, if you have a MySQL and you have a master and you have a few replicas, you can define stateful set for the master and a deployment for the replicas. So you always know that db1.mysql is always a master, and the replicas can change their name and they're fine. But that means that there are a few concerns, a few things that Kubernetes needs to ensure to guarantee that there is only one pod happening or one pod being scheduled. If you think how deployments work, if you tell Kubernetes, I want 5 replicas of this Nginx deployment or this Nginx pod, it's going to start all of those replicas of the web server. What happens if you kill one of them is Kubernetes automatically will start another one. It doesn't really care how they look like. They are stateless applications. What happens with a stateful set? Try to access a database from 2 different places. You're going to break the file system. You're going to break the database. And I'm talking about databases, but I can talk about Elasticsearch, Kafka, any kind of queue, Redis. I'm talking about these kind of applications that have state, but we cannot be that. We cannot shoot them and start another one without the first one stopping properly, right? This is actually can be catastrophic. So first, we have in this particular case our rancher cluster with our Kubernetes deployed. We deployed our MySQL. That MySQL needs a persistent volume claim. That data is going to live in that node. If we use GP2, for instance, or Google Disk or Azure Disk, it's going to be the same principle. The data lives in one node. So that pod that starts as an application is requesting a claim of X amount of gigabytes, and that data is going to stay in that node. But what happens if we lose that node? Well, the first thing that will happen is that the data is inaccessible. Yeah, this is pretty obvious, but if you think about remote storage systems like NFS or exported cluster exported cluster file systems, you will be able to access through a network, but the data is not close to the application. So in this particular case, we have the data there. We can access data if we use GP2 or host tier or anything alike, right? So accessibility is a big problem. So what could happen is, okay, now data is not accessible. I cannot access it through any other node, but actually my application is down. What's finished to my application is that the pod can actually not finish because it's going to stay in terminating state or in completed state. Why? Because Kubernetes cannot know if that node is down or that node is partitioned, if it is isolated from the network. And because it cannot know, the control plane of Kubernetes will decide to do nothing, right? And when you do nothing, it's like, okay, I do nothing. Maybe that node is partitioned and the application keeps working. I don't touch it. Well, that's problematic because if it's not a partition, if it's a node failure, let's say a power outage, the Docker daemon went down or the container runtime went down, or anything alike happen, your pod will stay in terminating state. Why? Because the control plane cannot, the Kubernetes control plane cannot communicate to that kubelet, to that node, and cannot tell the kubelet, hey, stop this pod. Therefore, cannot verify that that pod is not running, and it cannot use that pod somewhere else. So it cannot start that db1.mysql or db1 actually in another node because it cannot guarantee that the first node was stopped, the first pod was stopped, and therefore it's going to stay in terminating state. Why? Because after a timeout, it was, and actually by default is 5 minutes, the control plane will mark that in terminating state and will say, look, when you come back up, the node that now is down, you will reconcile, you will shoot the pod, and it will start somewhere else. But what happens if the node is completely lost? It's completely down, you will not be able to access this data or reschedule the pod. Moreover, we have the situation where any application requires high availability, requires production accessibility. We need to recover fast, and we need our system to self-recover. So in case that we go and say, okay, no, control plane, Kubernetes, kill this pod. I don't mind that it's isolated, and you as an operator go to Kubernetes and say, terminate this pod, kubectl, delete pod, -- force, grace period 0, delete this. And now, yes, it's going to start somewhere else, and it's going to reschedule the pod, but the pod is going to stay in pending. Why? Because the data is in that node that is down. You cannot start the pod somewhere else. Well, yeah, the EBS in this particular case, or the host there, is in that node. You could manually go and unplug the TBS and put it somewhere else. Yeah, good luck doing this at 3 a.m. in the morning. So we have a big problem here. And the big problem is called service downtime. We cannot afford to have service downtime. So actually, let's go to the command line and do something like that. I'm going to use this same cluster that we had before. I'm going to provision a MySQL with the GP2. Here we are. And now I'm going to show you a bit of what I'm actually creating. The interesting point here about aside of the service account and conflict and etc. is actually the stateful set. So if for you guys that are not completely familiar with it, it looks like a deployment is very similar to deployment. We have the pod template in there. We can define the amount of replicas that we want to run. We deploy a normal MySQL image, and at the very end, we add what we call the volume claim template. That will map that pod to a volume. So the template, it will template. So if you have one replica, you have one volume that maps /0 and /0, -0 and -0. And if you add one more replica, you're gonna be able to map pods and volume. And does that for you automatically. This is fantastic, right? And by the way, we're mounting this volume into the MySQL directory. But we have a MySQL -0, and actually we have a PVC that maps that data MySQL -0. Storage class GP2 is an EBS. It has provision. It takes a while usually to provision, but usually today we were lucky, and that was fast enough. So now we have a database up and running, MySQL -0, that maps to data -MySQL -0. Let's check out where this actually pod lives. MySQL lives in 1141. Okay, let's go to the Rancher UI and make sure that the node is there. 1141 is just a worker, so I'm not. Okay, so let's go and just kill the node. Right. Before that, I'm just gonna make sure that you see what's happening. So now let's go, actions, terminate. It's gonna be lost for real. It's gone. Of course, if I lose a node, I could reattach the EBS and maybe I could be lucky, but we'll see that actually eventually that will fail and it will stay in pending. So this will take a couple of minutes because Kubernetes needs to time out and Amazon needs to fail the machine and everything. But actually, we can see if the node is down. This is the 1141. Here it is. You see here I had the 3 nodes, and one of them, the 1141, is already gone. Right? It's connection timeout. The Amazon sent the signal. Machine is down. Of course, Kubernetes haven't noticed yet. Again, this has a lot of timeouts, and it's usually a 5-minute timeout. It will fail faster than that. But pretty much we cannot access the database because the node is completely down. It's trying, pending, container creating. It's just not going to happen, right? It's going to stay in this forever. So this, we can stay here, but nothing is going to happen. It's going to stay here. Your service is down because it will not be able to attach this volume. So how we're trying to solve this, using StorageOS. First, instead of using disks that are ephemeral or that are being designed for virtual machines, what we're using is we're creating a virtual layer in between the storage, the physical storage, and what the container sees. The file system that is mounted in the container is handled by StorageOS, or actually the device is handled by StorageOS. So we provision a volume, then we have an application that wants to use this volume. That volume, in this case, we had 2 replicas to this volume. This is configurable in the PVC or in the storage class. And every time you write, that sends StorageOS manages the state and it replicates synchronously to different nodes, right? When those writes are happening and they happen in both replicas and the master, now the master can say, okay, this data is safe. I can give that back to the application. The file system gets the acknowledge and say, okay, I can keep going. Yes, of course, this adds latency for writes, obviously. But here, you can decide, by the way, how many replicas you want. If you don't want replicas, you don't trade that. So here, what we're doing is we need to make sure that our data is available at any time and at any point in time that the data is completely accessible, so we can fail it over in case of failure. So if that node goes down where the primary was living, meaning all the data of that MySQL was living in that node as well, we automatically promote the replica to be a primary. The container itself, the file system that is mounted to that MySQL sees nothing because we're handling that under the hood and say, okay, you're reading and writing from here now. And because there is one replica missing, we start syncing another one. And while this syncing is happening, yes, you can keep using your volume, no problem. And when when the replica is actually up to date, we'll add this replica in the list of healthy replicas. Okay, now everything has to be in sync, and we do the synchronous replication at that point. And yeah, you can control how many replicas you can tolerate for failure, etc. In the case that you want your volume to go read-only. So actually, I can do that. Let's do that. I'm going to use my second cluster now because I deploy StorageOS in a slightly more robust way rather than the default easy friction one. So in here, we have our second cluster. Let me show you. By the way, the node is down. T2. Now T1, similar as before. 4 nodes, and now this one has one etcd, a couple of control planes, but also the workers. Let's check StorageOS. Nodes. By the way, this StorageOS UI, it serves in the 5705 on any of the nodes that deploys that pod. That's the daemon set, so any of the workers. So now we have the 4 nodes. So we can see, for instance, that every node has 48 gigs of data, available capacity, that all aggregate into one big pool. You can start segmenting nodes where you want the volumes to live, and you can have all these decisions about where you place data, right? But here today we're talking more about what is a problem with the stateful set. So I deployed the same example with MySQL, but instead of using GP2, I was using StorageOS class. Let me show you. Same as before, it's in a different cluster, but now the persistent volume claim is mapped to StorageOS class, right? It's the only thing you have to do. It doesn't really matter which provisioner you use. For the YAML point of view, the only thing you have to do is change one name. And that storage class, by default, is telling StorageOS to add a replica for this volume. So by default, it's 0 replicas, which means there is one instance of the data in the master, or the primary volume, as we call it. And because now there is one replica, we'll have a second copy, a full copy of the data in sync in a different node. So let's check that out, actually. StorageOS, by the way, maps automatically the namespaces of Kubernetes to the StorageOS control plane. So every time you provision a persistent volume claim in a namespace that was not used before by StorageOS, we create that namespace. So in the MySQL namespace, we have a volume that actually has one replica. This volume, the master location, is living in node 140. Let's check out where the replica is living. So 140 the master, 133 the replica. And actually here, check out that we haven't mentioned where the MySQL actually is running. And that means that, yes, StorageOS is handling the network connectivity. So whether the application lives in 140 or not, it doesn't really matter because StorageOS is giving the access. Of course, it matters for terms of performance, and we're going to talk about that later because I'm actually very excited to talk about the cellular extender that we have implemented. So there are 2 strategies here to solve the problem we were talking before. 1, we need to access data even the node is down, and 2, we need to be able to tell Kubernetes, hey, by the way, my data is there, try to put the container there because there is lower latency, everything needs to be faster. So, okay, let's go to node 140 and start doing things to it. But before, let's add a bit of data into the MySQL. Actually, let's use a client. Yeah, sorry, my mistake. Nah, sorry guys. Typing when 200 people is watching is not that easy. So I'm using now just a tiny container to show you actually how you access to stateful sets. So how I'm going to access that stateful set is just in the same namespace. Therefore, I can use just this host. Look, MySQL -0 dot MySQL. That's it. There is a service name called MySQL. It's a headless service. If you have heard about it, it's designed for stateful sets. So now I can just access that MySQL. I probably create this shop. Now it's gonna work. Insert into. Cool. What I just did is just adding some random data, completely irrelevant. So just a bit of data, nothing important, but this is going to help us to check out later when things happen to see actually that MySQL is completely healthy because we will actually check the data. And we're back. Cool. So now we have the data. Let's check where the MySQL lives. See, MySQL lives in node 1054. As we said before, master volume is in 140. So yes, in this particular case, we're accessing the network. And yes, you can control it if you want this to happen, or you can just descheduler to the side. So now I'm just going to trigger the same behavior that happens with a health check failure. And actually, because later on I'm going to shoot the node as well, as I did before with the other cluster, I want the cluster to stay a bit stable for now. So I'm just going to trigger the same behavior that will, the same code path actually, that will trigger a health check failure on the StorageOS health checks. So StorageOS between container or between nodes checks if those volumes are healthy. So in the node 140, this one, we have a master volume, this one. And then on the node 133, we have the replica, right? Cool. And the other nodes don't have volumes. So check this out. I'm going to drain the StorageOS volumes on that node and see what happens. So the same that if the health check fails, this node is not healthy anymore, the 140 is not healthy anymore. Look, it actually automatically promoted that replica to a master, and it created a second replica because this is the declarative, right? We won for this amount of healthy replicas, and this node is actually going to go down eventually. You better take care of it. So we go to the volumes now. And because there is barely amount of data, it is already healthy, meaning it already synced. So now the master location, as I said before, is in 133. Cool. Let's check out the MySQL again. Oh, sorry, my bad. The data is just accessible. And even the data now is being read and written to a different master place. Actually, data is available. It's like, okay, we have trained the master node, but actually the file didn't need to restart the MySQL, didn't need to restart the file system, didn't need to do anything. The MySQL itself, doesn't see anything. Of course, in terms of failure, it takes around 100 milliseconds to make sure that we passes all the that doesn't pass all the health checks, promote, and everything. So if you're writing constantly to that database at a full speed, you will have a lag of hanging connections, maybe for 50, 100 milliseconds, and then it will unleash again and start writing again. So, okay, cool. Let's go back. We are talking about accessibility and automatic failover, right? But this is not everything. This is not enough. This solves a big problem for high availability and actually operability for your cluster. But there is something that actually I'm announcing today, which is called fencing. Fencing is already released in our product, but it's something we're still showing to people. You know, we were mentioning that Kubernetes cannot tell if a node is partitioned or is down. Well, how do we fix this? Well, StorageOS has health checks. StorageOS, in between nodes that are not dependent to Kubernetes, StorageOS knows that if you have a volume in a specific node where that application is mounting that volume in that specific node and is replicated and is synchronously replicated, you don't really mind if the node is partitioned from the network, is isolated, or is down. The problem is the same. Hey, you have a primary volume that needs to be replicated at every single point in time, and actually it's not, because it's either down or partitioned. So when that happens, because StorageOS has automatic failover, and you can access the data, or you can mount that StorageOS volume from anywhere in your cluster, it doesn't really matter. So if that node goes down, StorageOS has a functionality that actually I'm labeling that stateful pod, that MySQL pod, and say to StorageOS, hey, if you see this node or this node going down, or the node where this pod is going down, make sure that this pod starts again. And it goes to Kubernetes and it tells to Kubernetes, hey, you have to shoot this pod, make it start somewhere else. Because as provisioners of the storage, we know that this can be done. This needs to be done, in fact. So this is something that relates a lot on timings and things like that, but I'm going to do a live demo. Let's go for it. So let's label the volume. And of course, you can do this at the provisioning. I'm just doing that for the dramatic effect, but of course, you can add this label in the StatefulSets manifest. Let's double check. So we can see that the label is applied. So pretty much what's going to happen is when the node is down, StorageOS will check for the pods in that node. It will ask Kubernetes, hey, give me from that node any pod that has this label. And if that's the case and it finds one, it's going to tell Kubernetes, hey, shoot it. Let's check where the MySQL actually is living again. It's living in node 54. Node 54. So node 54 is a worker. We're not gonna break anything. Actually, let me double check. Oh, sorry guys. Here, 1054. Cool. That was not enough. T1. Yeah, here it is. 1054. Right. Terminate. Yep, just get it out, shutting down. Actually, in the meantime, and actually, by the way, because Kubernetes takes a while to figure that out because of timeouts, maybe the node is healthy, but StorageOS will detect that it's not when it goes down. So it's shutting down. We can go to the StorageOS one. I'm going to make sure that I'm not accessing the node that I just turned down, but let's go. Here it is. The node is offline, right? StorageOS has failed the health check and is saying, oh, okay, this node is down, and it takes anything that was in this node and it will promote the next one. Actually, you can see here that the MySQL has actually moved from the node. It was not before in node 54, and now is node in 172. Cool. That logic is implemented by one of the StorageOS containers. And what pretty much happens is there is what we call a CSI, or what is called a CSI attacher, that attach the volume to a specific node. So we're telling this attach, hey, this is no longer valid, and this is going to happen with a bit of time. So now most likely it's downloading the MySQL image and doing all that lifting. In the meantime, you can see the node isn't available. The way this happens, I just want to talk about the next thing, is that, and actually I'm going to finish with this because we're a bit short now on time. I'm talking a bit too much maybe, but pretty much now we have seen that StorageOS can handle where things are running. It can handle failures of the nodes, but there is actually one really important point that we haven't talked is like, hey, data can be big and it can take a while to move data around, but containers move actually real fast. So we have implemented, and this is in tech preview in the current release of StorageOS, and I wanted to show you that today, but it's more than fine. So pretty much what we're doing is telling Kubernetes where the data is living. So Kubernetes has to provision a pod, and we say, hey, Kubernetes, the data is there. If you can, provision it there. And this is implemented through what we call a StorageOS scheduler, which pretty much is an extension of the Kubernetes scheduler. So let's go check this, how this is going. Look, the MySQL is up and running in the time I talk about one slide, which we were talking about 40 seconds. So actually, we decreased from 5 minutes to being down and not being access, not have access to data, to the MySQL that actually started in a different pod. And this happened because StorageOS had told Kubernetes, should that pod start that somewhere else. So again, let's check the data. But hold on, I killed a node where that client was there, and now it's hanging. Sorry, 1 second. It's hanging. Let me create a new one. But we want to access T1. Okay, actually, let's check this out. Not ready. And here's the data. So we can start from different nodes. StorageOS talks to Kubernetes. It tells shoot the pod, start somewhere else, data is safe, you can start. We have fixed actually a big problem. So going back here, let me check the time. We're 10 minutes out. Let's move on the questions. So as a recap, I'm just going to leave that here, but I'm going to start answering questions. So let's check that out. Let me give back access as well to Adrian.
You don't have to give me back access yet, because there are questions and you're probably going to have to demo stuff. So I only have one slide left that says that the whole webinar is over, so we can wait. Dude, that was amazing. I got to tell you, watching your demonstration, is it not immensely satisfying to just go find nodes and just shoot them and just know that everything's going to be fine?
Yeah, it's cool.
It's so awesome. It's one of my favorite things to do through the Amazon UI. Like, you know what? I don't really like the way you're behaving. I'm just going to turn you off.
What
and
can
everything just
possibly go
recovers.
wrong, right?
So we have a few questions. Some of them are a little more complicated than others, but if any of you have questions, now's the time to get them in, because if we run out of questions, well, we'll just end the webinar. So first of all, we have a question from Janet, who says that this is very, very interesting, but wants to know if the, hang on, let me find the original question. It was like stretched out over several. There. If slave replication lags, and here we're talking about replication at the StorageOS layer, not at the MySQL layer, what would be the effect on the primary? And for a little more context, they have very busy databases doing at least 500 transactions a second, and they're concerned about replication lag if a slave starts to fall behind.
Yeah, that's actually a really good question. I should have mentioned that before. So how does latency affects that when we write is based on pretty much effects on writes. So writes have the latency to go to, and as I said before, they are synchronous replicated, and you are worried of what happens if that synchronicity goes higher. So first, we StorageOS have a write through cache in the container as well. So all the reads are not only served from the local disk or the primary volume, but also if they're fully remote, they're served from hot data. Second point, in terms of latency, usually Amazon in this case has a 2 millisecond delay in between availability zones, right? In one, and we're talking about this is like 200 times longer in terms of time than in the same availability zone usually. If that lags and decreases, your writes will be affected. Yes, to the point that at some point this replica may go down, and StorageOS is a bit aggressive in terms of health checking. So if that node starts being, the node where the replica is living, starts being super loaded and cannot keep up, StorageOS will mark that as, hey, this node is unhealthy, and most likely will start replicating to a different node. If this is a really catastrophic situation, right? That your data cannot be written to the replica. For instance, in Google Cloud, the latency in between data centers or availability zones is 0.5 milliseconds. So it's real fast. That is not a problem at all in terms of latency. If you have big workloads, yeah, put things in as close as possible. Latency affects you. So eventually we will mark that replica down. Also, just to finish this question, if you can decide how many replicas you can have unhealthy for a volume to go read-only. So we have a protection system that says, look, if you have 2 replicas and 1 primary, and you lose 1 replica by default, it's okay, we will create another one. But if you lose the second one during that time, we will put the volume in read-only. So you cannot keep writing in there, you can keep reading, or you can say, no, try to keep the replicas as much as possible, but don't fail the primary volume if the replicas are unhealthy. So it's a way for you to control the consistency of the data or the availability of the data. Is the CAP theorem that probably most of us are working day in, day out.
So continuing with the same model, but rather than being cloud-based, if somebody had Kubernetes deployed on-prem, first of all, StorageOS will work fine on-prem in an on-prem Kubernetes cluster, right?
Yeah, that's correct. Pretty much. Yeah. Sorry, go
on. I was just gonna. Second part of that question was if they were using a SAN on-prem, then most of those latency questions go away as far as the inter-AZ latency, right?
Mm-hmm. So StorageOS, we try to do this and build that being very, very agnostic of the backend. So what we're doing is this layer in the middle between hard disk backends and frontend. So as soon as you have a Linux file system that you can give to StorageOS, we will use that. And the way we do that is by isolating the volumes, what we call blob files. Blob files are flat files. Actually, let me show you that super, super fast.
You don't have to go super fast. We've still got 35 minutes blocked out for this, and we'll go longer if we need to. So there's only like 8 more questions, maybe.
Hopefully we have data in this node. Yeah, we have data. So you can see here that for 1 volume, we have two blob files, and we can have as many as we need. And in this particular case, this is a machine that has the root file system from an EBS mounted here, right? So this is your root file system. The blob files are written there. This is where physically StorageOS is writing the byte level data. But what happens if you have your SAN? So the only thing you have to do, and actually sometimes I do this exercise where we plug another EBS, we create another directory, and we mount the SAN or that EBS in dev2. Automatically, without any downtime or anything, StorageOS raises its capacity to that new disk or that new partition or that new storage endpoint available.
That's super cool. Because you're using disks that are formatted and mounted at a mount point, does StorageOS have the ability to use just raw block devices that are connected but not mounted?
No, and the reason actually, yes and no, but no in production to make sure that that you are agnostic from the provider. So if you have, for instance, a VMware VMDK, create a file system there, plug it, give it to us. So instead of implementing 25 different drivers that might work well or not, we have decided that it could be easier for everyone in that particular case. But we're listening to the community as well, and we're looking into adding some drivers that automatically raw blocks can be mounted or formatted.
Cool.
And
so we have a question.
Usually,
yeah. Go ahead. Sorry, I thought you were done. Please.
Yeah. Usually this question comes along as well with something that is interesting. That is what happens with these applications that write specific system calls to the file system. Do they apply to the underlying file system? And the answer is yes. We pick up those kernel system calls and we apply them properly according to the to the call that is sent from the application itself.
Nice. You had the web interface open on one of those tabs, right? The dashboard.
Mm-hmm.
Can you just jump back over there real quick?
Yeah, here we are.
Yeah, you were jumping back and forth between the Rancher tab and
mm-hmm.
this. This is actually, so Edgar's had a question about if it had a UI, and this is the actual StorageOS UI, which is separate from the Rancher UI.
Yeah, that's correct.
Okay, cool.
That's correct. At any of the nodes that I started at the port 5705, we run the API. And the API, if you access to the browser, it will give access to this. It's the same data. It's REST-based data that you can access through the CLI, the StorageOS CLI, this API, or integrated through other systems. Kubernetes is one of them. But actually, we're looking into the Rancher UI as well to be able to work on that API.
Right. Nice.
Mm-hmm.
So let's scroll back here and... All right, so Anil had a question that we may have just answered with the block devices question, but he's asking if he was asking me about various types of Kubernetes volume support. Sorry, it's one of those ones that has like 4 questions, so I'm trying to consolidate it into one. And yeah, actually, so Anil, just your question ended up with, can we use both StorageOS and direct volumes from like Amazon, for example? And there's nothing, because this is a storage class, you could theoretically have a storage class for each, and then the people who are deploying the workloads could use whichever they wanted, right?
Yeah, definitely, Adrian. That's a really good answer. And in fact, because of Kubernetes is such a very, actually is designed a beautiful way in terms of isolation of concerns from a development point of view. Yes, it's just a storage class. So you can coexist, no problem. You can have a few volumes with GP2, a few volumes with provision IOPS, a few volumes with StorageOS if you want. It's completely up to you, no problem.
For me, as an operations person, I'm not a developer, but I'm the guy that builds and manages these clusters. I like that Kubernetes lets me make storage classes available for different, literally, classes of storage. So I can have, some magnetic disks that are low IOPS for people to use for dev projects, and then have the really expensive disks limited for certain specific types of stuff. But then I don't have to worry about provisioning those volumes. The people who are launching databases know that they can use fast storage versus developers using slow storage. And hopefully we don't have developers launching development apps on fast storage, otherwise we're gonna have to have a talk.
Yeah, that's actually, if you guys remember from the very beginning of the slides, we were talking about the storage classes, an administrator thing, right, Adrian? So you as an administrator can create different storage classes and maybe give access to those classes according to which role in the company you have or which role as a developer you have. So actually, we work very close with the Kubernetes maintainers, and actually some of our engineers maintain code in there as well for the storage parts and the panels. And actually, one of the things that come up a few times is that from a Kubernetes point of view, not only you have one storage class for each provider, but every provider can have as many storage classes as you want. As I showed you today, you can have a few storage classes that actually they are all StorageOS, or they're like 5 storage classes for StorageOS. One is for staging, and it disables replication. Maybe one is for production, and it enables a couple of replicas. Maybe another one is called for some security with sensible security issues, and you want to enable encryption by default. So you just add these in the storage class parameters, and your volumes just need to reference that, and that logic, that functionality comes by default.
Nice. That's awesome. Edgar's has a follow-up question where he's asking if you guys support resizing volumes after they've been created.
We have put the code in 1.15. It went in, so we wanted to put that code in the 1.14 of Kubernetes. In the end, it passed the cut in 1.15. For the Kubernetes part to resize, and for CSI, which is the new standard, that's not implemented that yet. But the StorageOS part is ready to resize those volumes. There are some interfaces with Kubernetes that are still not ready. So we're doing all the plumbing in there to make it ready. So it's going to be available soon-ish, I could say in the next quarter, few months, something like that.
Nice. Something to keep an eye out for.
Yep.
Josh is asking what types of state engines or databases or persistent stores have been tested with StorageOS? Is that something maybe that's on your website, or can you just rattle off a few?
Yeah, definitely. We have a use case page in the docs. Also in that repository I was using today, there are all the YAMLs in there. So if you want to use that MySQL I used, or you want to use Elasticsearch, all the YAMLs are there. You can just go and just blow that, and it's going to work. So pretty much we focus a lot on databases and stateful applications such as Elasticsearch, MySQL, Postgres, Redis, Cassandra's. We have worked a lot with MongoDB and Kafka as well. So for instance, let me go in detail here. Databases, normal relational databases uses usually 4K blocks to write to the kernel. And we optimized initially a couple of years ago. We were working very hard on that. Lately, we have realized that actually Kafka writes at big blocks of 256. And we optimized, and a few versions ago, we started adding optimizations for these specific block types. So for different block sizes, now we are also way, way better. For instance, in Amazon, you have 3,000 IOPS provision for your EBS. You want to max that because it's the backend output or the backend disk. So with bigger blocks, you get way better bandwidth than IOPS. The IOPS are fixed, but not the bandwidth, right? And the bandwidth is actually defined by the size of the nodes. So pretty much we have worked with different stateful applications that are very used in the market, and we're tuning StorageOS to adapt to them and tune to them more and more.
Fantastic. There's a follow-up question, and maybe this is on the page that you referred to. Do you guys have any benchmarking information up about throughput and performance metrics for writes and reads?
We have performance metrics not published to the internet. It's very internal, and we usually share them. We're more than happy to share them, but we don't put them public for the simple reason anyone that works with a bit of storage knows that it depends a lot on what you're using, how are you using it, how are you measuring it, what are the metrics, for instance, machine types, machine sizes, bandwidth capacity, all that stuff, right? So if you guys won't really know these kind of things, we have two approaches here. One, contact me or contact us through Slack channels, storageos.slack.com, or email me, and we're more than happy to share these kind of things, but we want to be meaningful in the way we share it. Or, as I showed you today, starting it is very simple. And one of my colleagues usually says, and I actually like that point, like, you know what, run it, bench it. We have in that repository I was using today an FIO profiles and FIO examples in there and provisioners for Kubernetes. You can run there, and FIO is a fantastic tool. I actually built some examples that provision pods with multiple volumes or one pod with many volumes mounted, etc., and run all these stress tests. So yeah, that's it.
Does StorageOS have anything for snapshots or any type of extraction of the data to build new replicas from it? Anything of that nature?
So we don't have snapshots, and there is a decision here to be made, and let me spend 1 minute about this. Snapshots is something we were considering a lot, and we were thinking our roadmap, and we were gathering information from the community, and it's like, okay, what snapshots are used is usually to keep state of data and back the data. But in the end, what people want is recovery of the data more than snapshots. And what we have found is that snapshots don't work for a lot of applications. For instance, if you have a Cassandra and you have different parts of the cluster and you snapshot it, you will have a big problem because you will not be able to recover that data. For MySQL, usually works fine, but you have to freeze the file system. We want to be agnostic to the file system. So snapshots is usually something is controversial. So we don't support snapshots. We're thinking about it for some of the use cases. We usually recommend Velero, which is a project, is a 1.0 project now under the CNCF, which is for backups. It's a tool developed by Histio, and initially it was called Arc. Now it's called Velero. It works fairly well. Their integration with Restic, and with that you can be successful in terms of getting the data from the PVCs, the StorageOS PVCs as well, actually backing up in an object store like MiniIO or S3, and from there it's very easy to recover as well. There are a few things that needs to be polished, but it's a really interesting project that we recommend a lot for backups.
Cool. The last question that we have is from Edgar's, and he's asking if, well, it says, how much time does it take for Kubernetes to unbind a StorageOS volume when the pod is killed so that a new pod can mount or bind it? You mentioned that there were some timeouts associated. Do you know what those defaults are, and can they be configured?
Yep. There are different timeouts here. One is the timeout that the control plane of Kubernetes will mark a node as down, and that is 5 minutes. By default, you can change that on when you bootstrap the cluster. There are a few configuration parameters you can pass to kubeadm, or the Rancher actually is really nice on the Rancher UI. You can actually define all these parameters. Then you have these 5 minutes. Then for every pod that is not marked as healthy, there is usually a taint that is decorated by Kubernetes. If you describe your pod, you will see that. You will see what I mean, that everyone has a default of 5 minutes. So if you go to your pods and do kubectl get pods with the YAML output, pipeless, and search for taints, you will see what I mean. It's going to do a no execute after 5 minutes. In terms of the mounts are a completely different thing. StatefulSets guarantee that the mounts are done in order and things are unmounted before it tries to mount. That's what I was talking about before between the deployment and StatefulSets. This is fundamental. StorageOS uses proper POSIX standard of Linux devices. So what the file system that MySQL sees inside the container is just a disk, a Linux normal device file mounted. So the time that it takes to unmount this is literally the same as if you go to the node and do umount this device. So if there are things syncing in the file system, it will finish syncing and clean up the mount. If there is nothing and everything is synced, it will just unmount, right? So it's exactly that. So the kubelet pretty much does is shoots the pod, finish the container, talks to Docker or the runtime that you're using, shoots the process, runs the unmount of the volume, and it's just a Linux unmount that succeeds. It says, okay, this is done. And now the scheduler can say, now you start somewhere else.
Okay. We have.
That was the last question, right, Adrian?
That was almost the last question. There's one more
Okay,
question that actually
cool.
dovetails in with the snapshot question that you asked or that you answered earlier, but it's specifically about disaster recovery.
Mm-hmm.
If we're using StorageOS volumes, what? So I know that you recommended just using whatever they renamed Arc2 to run backups. And if for some reason there is some type of data corruption that gets replicated across and the whole thing's down, can you just talk about the workflow that you would use to recover? For example, do you create new volumes and restore and remount? Can you kind of give an idea of what that process looks like without going into tremendous detail?
Mm-hmm. So there are two strategies here. One is usually stateful applications require that you use the tools of that application to backup. So again, you use MySQL dumps or the Percona extra backups that work a bit better than the dumps, or you use the snapshots for etcd, or you use things like that. You will create new volumes and recover from that. What we have seen, and Restic and Velero do that, is they create init containers on your stateful sets, that those init containers pull those backups, add all that information in the right place, sharing the file system to the main container. When the init container is finished, the main container starts and it recovers. So if you want something that needs to be really, really recoverable to fault tolerance, and we're talking about, hey, you have two replicas, you have to lose 3 nodes to lose all your data at the same time. So,
Mm-hmm.
and if you have up to 5 replicas, you would have to lose 6 nodes if you have 5 replicas at the same time to lose your data. So in that particular case, that everything goes really, really bad, you could recover from a database, and you could do that either with init containers or start your application. And in the same way you could do with the initial problem I show you, in terms of the stateful set, saying, hey, the EBS is gone or the host is gone, how do you recover from a normal backup from the application itself?
Right. Cool. Okay, that was the last question. Do you have anything else that you want to show before I take control again and we wrap this up?
Sure. I just want to thank you everyone for coming. Thank you, Adrian and Rancher, for giving us the opportunity to talk about this. It's awesome, and I'm very happy about this. Also, we haven't talked about monitoring, but we have a Prometheus endpoint and full-fledged of metrics and stuff like that that we can go through other day. Also, contact us if you want to try anything you need. Just we're very open about things. Just come and feel free to join the Slack channel and just throw questions and everything you need. So thank you very much, and thank you,
And
Adrian, as well.
oh, dude, it's great to have you here. If any of you are at any conference like KubeCon coming up or any event where the StorageOS people are there, swing by their booth and just ask them to give you a demo. I found them to be super friendly, super approachable, and all they want to do is show you how awesome this technology is. Because like we should all be super excited that we have all of these toys to play with every single day, and that we get paid to do so. So swing by their booth and ask them any question that you want. So let me jump back to my last very exciting slide, which says thank you very much. I see that lots of people are already dropping off. We have these master classes every week or 2 weeks. Join. Thank you all for coming. I hope that it was useful for you, and go out, run StorageOS, and start playing with some volumes. Have a great day.
See you. Bye.
Bye.